On the 13th of April 2029, Apophis will pass by Earth at a distance closer than many of the satellites humans still use every day. About 340 meters wide, this asteroid is large enough to turn that close approach into a rare event in the sky. Apophis will not hit Earth, but once the risk of impact is ruled out, the real question begins to appear. Measurements show that Apophis may not be a solid block of rock racing through space, but a loose structure, full of empty spaces held together by extremely weak gravity. The asteroid's motion is also unstable. Instead of rotating neatly around a single axis, Apophis tumbles, stretches out, and narrows at the middle, as if two parts once collided and then became caught together in space. When it passes close to Earth, our planet's gravity may do what distant telescopes have never been able to do. That close flyby may force Apophis to reveal just how weak its interior really is. Apophis is not a name that has only appeared in recent years. This asteroid was discovered in 2004. As near-Earth object tracking systems were becoming more accurate. At first, Apophis was only a very small point of light moving among the background stars. But when the first observations were entered into orbital models, this name quickly moved beyond the ordinary list and became one of the most closely tracked objects. The reason was not only its size. The solar system contains many asteroids larger than Apophis. What made this object different was the path once calculated for it. In the early models, the probability of an impact with Earth on the 13th of April 2029 once rose to about 2.7%. That number may sound small in everyday life, but for an object about 340 meters wide, this was not a level of risk that could be ignored. An asteroid 340 meters wide is still large enough to cause serious consequences if an impact were to happen. Size is only one part of the problem. The rest lies in speed. When a mass of this scale enters the atmosphere at tens of kilometers per second, the impact energy would go far beyond what ordinary human intuition can imagine. So, for a short time, Apophis represented a very direct question. If an object large enough is discovered while its orbit still contains uncertainty, how much time do humans have to correctly understand that danger? But science does not stop at the first calculations. Each time Apophis was observed again, the asteroid's orbit was narrowed down with greater precision. The uncertain regions gradually disappeared. By 2021, radar observations had helped remeasure Apophis's path with far greater accuracy than the early data. When the observation points became dense enough, the answer about the impact risk became clearer. Apophis will not hit Earth during its close flyby in 2029. The possibilities once mentioned for later returns, such as 2036 and 2068, were also ruled out when the orbit was recalculated from new data. This story is not a warning about an approaching disaster. The impact risk has been ruled out with high confidence for at least the next 100 years. But as the orbit became clearer, attention began shifting from the path to the body of Apophis itself. This asteroid will pass by Earth on the 13th of April 2029, at a distance closer than the orbits of many communication and weather satellites. But knowing the orbit is not the same as understanding the nature of the object traveling along that orbit. An asteroid is not just a point on a map of space. Apophis has a shape, mass, density, rotation, surface, empty spaces, and an internal structure that we still cannot see directly from Earth. That gap is what makes the 2029 flyby so special. After the impact risk was ruled out, the focus shifted to another question. If Apophis truly passes close to Earth as the models predict, our planet's gravity will act on a body whose interior may not be solid at all. At that moment, what matters is no longer whether Apophis will miss Earth. What matters is how this asteroid will respond as it passes through the gravitational field of a large planet. A solid object may simply pass by and continue on its journey. But if Apophis is a weak, hollow, and uneven structure, this close approach could become a natural test. Not a test of Earth's survival, but a test of the asteroid's own structure. The deeper question is what Apophis is really made of. So far, no spacecraft has flown close to Apophis for us to see each rock on its surface clearly. The first clue comes from a less visual but very important measurement: density. For an asteroid, density does not only tell us how heavy the object is, it tells us whether the mass inside has been compressed into a solid body. Apophis is estimated to have a density of only about 1.75 grams per cubic centimeter, significantly lower than the density of solid rock material. That number changes the way we look at an asteroid about 340 meters wide. Apophis no longer looks like a solid mountain thrown into space. A more reasonable explanation is that its interior contains many empty spaces, a lot of loose material, and a structure that is not as continuous as the outside of a rock might suggest. That is why Apophis is often viewed as a candidate in the rubble pile category. Put more simply, it may be a pile of broken rocks holding itself together. It's not an intact block or a hard core wrapped in a thin layer of dust, but a collection of rocks, pebbles, dust, and fragments held together mainly by extremely weak gravity. For Apophis, the estimated porosity may be around 40%. That number does not mean there is one giant hollow cavern inside. It only shows that there are many small gaps between the pieces of material, like a pile of rocks stacked together but never fitting perfectly. A structure like that will not respond the same way as a solid block of rock. If an outside force changes, the pieces inside may compress slightly, become wedged, slide, or rearrange themselves on a very small scale. On Earth, gravity presses everything down toward the ground. On Apophis, gravity is far weaker. A rock sitting on the surface is not held down as firmly as it would be on our planet. Even a much smaller disturbance may be enough to move material, especially if the surface is already close to an unstable state. But calling Apophis a pile of broken rocks does not mean this asteroid is about to fall apart. Apophis has existed long enough to maintain its current shape and orbit. That structure may be weak, but it is not necessarily chaotic. Many pieces of material may be temporarily locked into one another in a stable enough way, like a large pile of rocks lying still for a very long time, until a force strong enough changes the balance. We have seen this kind of object before in other asteroids. Itokawa, the target of the Hayabusa spacecraft, appeared as a rugged body assembled from many boulders and loose material. Bennu, where OSIRIS-REx once collected a sample, showed an even softer and more yielding surface than expected. When the spacecraft touched down on Bennu in 2020, the material beneath it did not react like hard bedrock. It almost sank inward, revealing that an asteroid can look solid from a distance but be very porous and weak when touched directly. Apophis has not been tested that way, so the internal structure of Apophis is still something that must be discussed with caution. What we do have are measurements of its size. estimated mass, density, radar signals, and rotation. From these data, the rubble pile model becomes a reasonable explanation. But no one has directly seen the empty spaces inside, or knows which regions are stronger and which regions are easier to shift. The year 2029 will bring that hypothesis closer to a real test. If Apophis is truly more porous and looser than it appears, its close flyby of Earth may leave traces small enough to be hard to see, but clear enough to measure. A change in rotation speed, a disturbed region on the surface, or a small amount of material sliding could all suggest that Apophis's interior is not as rigid as it looks. Apophis does not need to break apart to become a natural experiment. As long as it changes enough to be measured, the 2029 flyby could already tell humans much more about how a rubble pile asteroid holds its shape. From a distance, Apophis is only a point of light moving along the correct orbit. But inside, this asteroid may be a far looser structure, waiting for its closest approach to Earth to reveal its first weakness. Apophis does not appear as a neat, round block of rock, nor does it look like a simple meteorite fragment rotating in the dark. From radar data and shape models, this asteroid appears elongated, uneven, and narrower in the middle than at the two ends. The closest description is a two-lobed body, like two large masses of material that once touched and then continued existing together in a single structure. This detail does not only make Apophis look stranger, it changes the way scientists think about the asteroid's strength. For a solid block of rock, a distorted shape may simply be the trace of old impacts. For a rubble pile, the narrowed region in the middle carries a different meaning. It may be where two large sections are connected by loose material, weak friction, and small gravity. If all of Apophis is like a pile of material holding itself together, the connecting neck may be the first place to respond when an external force changes. So far, we still do not have a true close-up image of Apophis. The two-lobed shape does not come from a sharp shot like one taken when a spacecraft orbits an asteroid. It is inferred from radar data, reflected brightness, rotation, and reconstruction models. So this shape still contains uncertainty, but even with that uncertainty, Apophis still does not look like a simple sphere. Its elongated and uneven structure is already enough to make the 2029 flyby a special case. A narrow neck in a porous asteroid may act as the force transfer point between two large masses. When Apophis moves through ordinary space, that balance may not change much. The pieces of material hold one another in a stable enough state, but when the asteroid passes close to Earth, our planet's gravity will pull more strongly on the nearer part and more weakly on the farther part. That small difference does not need to tear Apophis apart. It only needs to be enough to stretch, compress, or slightly shift the neck region, and it could leave a trace. The two-lobed shape is not only a question of what Apophis looks like. A round and solid object would distribute force more evenly. An elongated object with two large ends and a narrow middle will have regions that experience force in more clearly different ways. If the models are correct, Apophis will not simply pass Earth like a silent stone. During the closest few hours, each part of that body will experience a different level of pull. The connecting neck may become the place that reveals how strong the internal structure really is. One possibility mentioned in the models is that Apophis once formed from two separate masses of material. They may have collided very slowly, not hard enough to destroy each other, and then stuck together through weak gravity. This kind of formation is called a contact binary, but for Apophis, this is still an interpretation from the available data, not a scene that has been directly observed. The exact past of Apophis remains uncertain, but its current shape is already enough to show that this asteroid may not be equally strong in every region. A body like that makes the question in 2029 more specific. Not whether Apophis will split in two. The more accurate question is whether the connecting neck will show any measurable change after the close flyby. Will the nearby surface be disturbed? Will the rotation after the close approach be different from before? If there is a change, even a small one, it will say much more about how the pieces of material inside are holding on to one another. That shape turns the 2029 flyby into a natural test. Earth does not need to touch Apophis. Our planet's gravitational field alone may place force on exactly the weakest part of that structure. If low density shows that Apophis contains many empty spaces, then the two-lobed shape shows where those spaces and loose materials may be tested first. The narrow region in the middle is not just a geometric feature. It may be the place where Apophis reveals its most fragile part. The shape shows that Apophis is uneven. The way this asteroid rotates makes that even clearer. Many objects in space, if they are not strongly disturbed for a long time, can rotate around a relatively stable axis. Apophis does not behave that way. Instead of spinning neatly around a fixed imaginary line, this asteroid tumbles. It rotates while also shifting its orientation, making its overall motion look like a body that has not fully found a state of balance. Observations show that this motion contains several overlapping rhythms. One main cycle lasts about 30.6 hours. On top of that rhythm, there is also a slower oscillation of about 263 hours. For an asteroid that cannot be opened up so we can observe its interior, rotation is one of the few signals that can reveal how its mass is distributed. A solid and uniform object usually rotates in a more predictable way. An elongated body with uneven mass and non-uniform structure will create more complex motion. Tumbling motion does not automatically prove that the interior of Apophis is shifting day by day. That would be too strong a conclusion for the data we currently have. What can be said more confidently is that its complex rotation fits the picture of a non-uniform object. Apophis does not appear to be a simple mass, with material distributed evenly from one end to the other. The motion itself suggests that the internal structure may be lopsided, porous, or assembled from regions with different levels of strength. That is why the rotational state of Apophis is not a minor detail in the data. A small change in the way it rotates may contain more information than its appearance suggests. If, after the 2029 close flyby, the rotation period changes, the spin direction shifts, or the level of tumbling differs from before, that signal will not only show that Earth has pulled on the asteroid, it will also show how that force traveled through the body of Apophis. A solid block would respond in one way. A weak and loose structure could respond in another. The year 2029 will give scientists a chance to test that motion through a natural influence from Earth. When Apophis passes close to our planet, gravity will not only pull on its orbit, it may also affect its rotation. No collision or explosion is needed. The different gravitational pull between the near side and the far side is enough to create a small torque on the entire body. For an object that is already tumbling, that change could become a measurable signal. Apophis does not rotate like an easily predictable object. When an asteroid already has complex motion, each region of its body will take turns passing through the direction of stronger force during the close flyby. The connecting neck, the two large lobes, the sloped sides, and the areas with loose material may all experience different conditions during the few hours closest to Earth. The question is not only whether Apophis will rotate faster or slower. The deeper question is what that change will reveal about how tightly the asteroid is held together inside. Models can predict a range of possibilities, but they cannot replace real observation. If Apophis changes very little, that would suggest its internal structure is stronger than it appears. If the rotation changes more strongly than predicted, this asteroid may be weaker, more lopsided, or looser than current models assume. Both outcomes have value. A quiet result is still data. A clear change would be a more direct sign that Apophis has been disturbed by Earth. Rotation, therefore, becomes one of the best ways to read Apophis from a distance. From the ground, humans will see only a point of light moving across the sky. In the data, that point of light is rolling, wobbling, and carrying the traces of an uneven structure. In 2029, when Earth's gravitational field touches that motion, Apophis may show how strong its interior really is without anyone needing to land on its surface. On the 13th of April, 2029, Apophis will not simply pass by Earth. This asteroid will enter a region where our planet's gravity is strong enough to create a difference between the two ends of the same body. The part facing Earth will be pulled more strongly, while the farther part will be pulled more weakly. That difference is tidal force. On Earth, tidal force is most familiar through the oceans. Sea levels rise and fall because the Moon and the Sun do not pull the entire planet with exactly the same strength. With the oceans, that effect creates tides. With an asteroid about 340 meters wide, porous, weak, and tumbling, the same principle becomes a structural test. Apophis will pass at an altitude of about 31,600 kilometers over the Atlantic Ocean. This distance is closer than geosynchronous orbit, where many communication and weather satellites still operate. In other words, Apophis will enter the region where humans have placed an entire layer of infrastructure around Earth. But unlike a satellite, this asteroid was not built to hold its shape. There is no metal frame, no rigid body, no control system. There are only rocks, dust, fragments, and weak gravity holding everything together. During the few hours around closest approach, Earth's pull will continuously change in direction and strength across the body of Apophis. Because this asteroid is tumbling, the same surface region may pass through different directions of force, one after another. A slope that has remained stable for millions of years may be placed under new conditions. A region of loose material may lose part of its delicate balance. The neck between the two lobes, if it is truly the weaker region, may experience a different kind of stretching and compression than the two larger ends. Tidal force is not like an impact. Earth will not strike Apophis. No surfaces will touch, and there will be no moment of shattering. The effect comes from the gravitational field far more quietly. But in celestial mechanics, a quiet force can still leave a trace if it acts on the right kind of object. A solid block of rock may pass through almost unchanged. A loose structure may respond with smaller changes, harder to see, but still measurable. The models do not need Apophis to break apart for this flyby to matter. The more important prediction is that its rotational state may change enough to be measured. Apophis may continue tumbling after 2029, but its rotation, rhythm, and spin direction may be different than before. This kind of signal cannot be seen with the naked eye, but it is extremely important. It tells us how the force from Earth traveled through the asteroid's body. The predicted physical deformation is much smaller than the exaggerated versions seen online. Models show that the body may bend or compress on a scale of only a few centimeters, mostly in an elastic way. After the pull decreases, the structure may nearly return to its original shape, but the surface does not necessarily have to remain completely quiet. On an object with weak gravity, loose material does not need a large force to shift. A small change in tilt or rotation speed may be enough to make rubble slide downward, exposing fresher material underneath. The important part lies in changes that are far smaller. Not a scene of Apophis being torn apart in space, but the possibility that an asteroid changes its own surface within a few hours because it passes too close to a large planet. If there are landslides, if new bright regions appear, if the rotation model after the close approach differs from before, humans will have real data on how a rubble pile responds when it is stretched. For most of observational astronomy, close approaches like this have happened without anyone being close enough, ready enough, or precise enough to record them. The year 2029 is different because Apophis has been tracked for many years before the event takes place. The orbit is clear, the timing is known. Telescopes, radar systems, and spacecraft can prepare in advance. This flyby is therefore like a natural experiment, scheduled many years ahead of time. Apophis does not need to threaten Earth to become important. An ancient, weak, and uneven object will pass through our planet's gravitational field close enough to be tested, but still far enough to survive and continue its journey. After that night, the question will no longer be only how close Apophis came. The question will be what Earth's pull left behind on the body of this asteroid. When an asteroid passes closer to Earth than the orbits of many satellites, the question that appears most easily is whether it will be torn apart. With Apophis, that question is not unreasonable. This object is not a solid block of rock. Earth's gravity will act on each part in ways that are not completely the same. The surface may change, and the rotation may shift. But between a body being stretched and a body being completely destroyed, there is a very large distance. Current models do not show that Apophis will split in two during its 2029 close flyby. The approach distance is very close by astronomical standards, but not close enough for Earth to tear this asteroid into many large pieces. The images, often imagined online, usually push the story further than the data allow. A weak object is not necessarily about to fall apart, and a porous structure does not mean it only needs to fly near Earth to be destroyed. Apophis may pass through a region that changes its own state, but not necessarily breaks its entire body apart. Tidal forces may create small deformation. Regions of loose material may slide slightly. Some parts of the surface may be disturbed if slope, rotation speed, and the direction of pull all push material out of its balanced state. Changes like these are important enough for science, but they are not the same as a scene of an asteroid exploding in space. One concept that often appears in exaggerated scenarios is the Roche limit. Put simply, it is the region where the tidal force of a large celestial body can overcome the binding force of a smaller body. If an object moves too close, especially when its internal structure is weak, it can be pulled apart. Apophis will not enter the distance that makes that scenario the main prediction. The 2029 flyby lies in a region close enough for scientists to pay attention, but not close enough to make disintegration a reasonable conclusion. Another concern is that material could separate and fall toward Earth. With the current data, this is also not the main scenario. If the surface is disturbed, small material may shift on the asteroid itself. But for large fragments to escape, enter a dangerous orbit, and then head toward Earth, far more conditions would be required. A small amount of rock sliding on the surface is not the same as creating a shower of material that threatens the planet. The truth lies somewhere in between. Apophis is not an impact threat in 2029, but it is still a rare opportunity to see what Earth's gravity can do to a weak object at a very close distance. The more important scenario is not splitting in two, but much smaller changes, such as a disturbed surface, a slight shift in rotational state, or a shape model after the flyby that is not exactly the same as before. A keyhole is another reason Apophis once drew attention. It can be understood simply as a very small region in space, where, if an asteroid passes through exactly the right position, Earth's gravity could bend its orbit in a way that makes a later return more dangerous. For Apophis, new observations have ruled out the dangerous paths that were once discussed. This result came from measuring the orbit more accurately over many years, especially through radar. So the keyhole remains an important concept in planetary defense, but it should not become the main fear in the current story of Apophis. It shows why astronomers must track near-Earth objects early. A small uncertainty in position can change the initial conclusion. But with the data we have now, Apophis is no longer an example of an object waiting to fall into that dangerous keyhole. It becomes an example of how continuous observation can turn an uncertain concern into a better understood orbit. The Moon is also not a forgotten factor. When Apophis passes through the Earth system, the Moon's gravity is already included in the orbital models. This is not a situation where just a little extra pull from the Moon could turn the path into an impact. Any significant uncertainty, if it remains, would lie in the observational data and dynamical models, not in an obvious factor that has been overlooked. The idea that a spacecraft could accidentally push Apophis off course also needs to be kept in the right perspective. Missions such as OSIRIS-APEX or Ramses are designed to observe, measure, and track natural changes after the close flyby. They are not missions to push the asteroid away from its orbit. Deflection tests like DART belong to a different story. For Apophis in 2029, the main force to observe is Earth's gravity, not the effect of a spacecraft. So the answer in this section is fairly clear. Apophis may change, but there is currently no evidence showing that this asteroid will break apart in a dangerous way. The more important scenario lies in small but measurable signs. A different rotation rhythm, a brighter surface region because older material has been disturbed, or a shape model after 2029 that is not exactly the same as before. Signs like these are not loud, but they are far more valuable than an exaggerated spectacle. Apophis does not need to be destroyed to tell us something. If this asteroid passes Earth and remains intact, that is also important data. If the surface changes, the data becomes even deeper. If the rotation shifts exactly as the models predict, scientists will have another way to test the strength of rubble pile asteroids. The year 2029 is not a test of whether Earth will survive. It is a test of how weak an object can be and still keep its shape after passing close to a large planet. The year 2029 is different from many asteroid close approaches to Earth because humans have time to prepare. Apophis will not appear unexpectedly just a few days before passing by. The time of closest approach is already known. The region of sky that needs to be watched has already been identified. The signs that need to be measured are also much clearer than they were in the early stage, when Apophis was still an orbital concern. On the ground, telescopes and radar systems will begin their work before Apophis passes by. They will track the asteroid's position, brightness, estimated shape, and rotational state at many different moments. Those data will not only confirm its path, they will create an initial reference point. If Apophis changes after the 13th of April 2029, scientists need to know its earlier state in order to compare. The changes they are looking for may be very small. A disturbed surface region does not necessarily create a clear spectacle in the sky. A change in rotational rhythm also cannot be seen with the naked eye, but in the data, small differences can become important traces. They show how Apophis absorbed Earth's pull and how the internal structure transmitted that force through the entire body. OSIRIS-APEX will have a special role after the close flyby. This is the continuation of the spacecraft that once brought samples from Bennu back to Earth. With Apophis, the mission is not to deflect the orbit or interfere with the asteroid. OSIRIS-APEX will arrive after Apophis has passed close to Earth to read the traces that remain. If the surface has been refreshed, The spacecraft may find brighter regions or material that has been less weathered. If the rotational state has changed, close measurements will help determine the exact level of that change. Osiris Apex is like someone arriving at the scene after the force has already passed through. Its value lies in what Apophis still carries on its surface and in its motion. A small slide, a shifted region of dust, or a difference in the rotation model could reveal more about the asteroid's strength than earlier distant observations. Ramses, the European mission aimed at Apophis, adds another layer of data. Instead of only looking after the event, Ramses is designed to study the asteroid before and during the close flyby. If deployed as planned, this mission could record Apophis's shape, surface, mass, density, porosity, and rotational state as it passes through the region where Earth's influence is strongest. Ramses is important because it creates a reference point before the event. Without data from before the close flyby, a change after 2029 could be mistaken for the result of better observation. With an earlier reference point, scientists will find it easier to separate what was already part of Apophis from the real traces left by its passage near Earth. When the different sources of data are placed side by side, 2029 is no longer just a beautiful observation in the sky. Ground-based telescopes will track the path and brightness. Radar will help refine the shape and rotational state. Ramses may record the asteroid during the phase when it is under strong influence. Osiris Apex will read what remains afterward. Each layer of observation answers one part, and when combined, they show how Apophis responded to Earth's pull. This also matters for other near-Earth asteroids. If one day humans have to deflect a dangerous object, knowing its orbit alone will not be enough. We will need to understand whether that object is solid or porous, strong or weak, a single body or assembled from many pieces. A force acting on a solid block of rock will not be the same as a force acting on a rubble pile. Apophis is not a target for a deflection test in 2029, but its natural response may help humans better understand objects of the same kind. For the public, Apophis will be a point of light moving across the sky. For science, it will be a rare measurement. An asteroid that once worried humans will return under safer, closer, and more carefully observed conditions than ever before. After 2029, the question will not only be how close Apophis came to Earth. The question will be how much it revealed about itself as it passed by. In 2029, Apophis will pass Earth safely. But what makes this close flyby remarkable is not the fear of impact. The real value lies in the chance to observe an asteroid about 340 meters wide, passing close enough for Earth's gravity to leave traces on its body. If Apophis truly is a rubble pile, a porous and weak structure held together by very small gravity, the changes after this close approach could say more about the asteroid's interior than any previous distant observation. A shifted rotation rhythm, a disturbed surface region, or a very small sign in its shape would be enough to turn 2029 into a rare natural test. On the 13th of April 2029, Apophis will pass through the sky as a safe point of light. But for science, it may be the moment when an object that once worried humans begins to reveal what it is really made of. Thank you for staying with Astrexo until the end of the journey. If this video helped you see Apophis in a clearer and calmer way, leave a like, share the video, and comment your thoughts below. I'll see you again on the next journey, when the night sky continues to remind us that some things pass very close, yet there is still so much we do not fully understand.